over again. So this is arc length. So if you have a parametric curve with x and y, the arc length is going to be given by this. And we could just leave it at that, but let's talk a little bit about why or how they got this formula, and then we'll take a look at an example. So this formula, the idea is that if you have a curve, and it doesn't have to follow any particular function rules or anything like that. Much like what you did in Calc 2, you have something, and then what you're going to do is you're going to take a look at a small piece of that, whatever it is you're looking for. We're looking for length, right? We're looking for the length of this curve, and we want a small piece of that. And so what we're going to do is we're going to break this up into little partitions, just like we did with finding the area under the curve. And then we're going to find the length of a small piece of this. And to simplify things, we'll just find the length of a line connecting 2 points. So what we would be interested in doing is finding the length of a line. And let's take this one line right here, say between x sub I and x sub I, or x sub I minus 1 and x sub I, the partition. I guess we should call t, I should say t sub I. And when I say t sub I, I mean the t value that you would put into the x and the y parametric equations to get your x, y value. So technically this point is, if we want to be really technical, x of t sub I minus 1, comma, y of t sub I minus 1, or yeah, y sub I of t minus 1. And then the other one would just be x sub I of t and y sub I of t. So what we would look at is the distance between those two points. You guys remember what the formula is for the distance between 2 points? Like if I have AB and CD, what's the distance between 2 points? Distance formula, remember? A minus, so the difference of the x's and the difference of the y, and then you square it. So the distance here will be x sub t sub I minus x t sub I minus 1 squared plus, and then y t sub I minus y t sub I minus 1. And all that under a square root. So we can look at this in a couple of different ways. And since we're not doing a formal proof, we're just kind of abuse some notation a little bit. And this is really the change in x's plus a change in y's. And since we will end up adding up a whole bunch of those, then this is just one of the deltas. And so what we could do is we can just say, oh, let's divide everything by dt, which is, again, not something that I would normally talk much about. But again, just to make our notation look nice, delta x dt, or delta t, delta y, delta t. And we can't just divide by dt, right? We have to multiply and divide by the same thing. So inside of the square root, we're actually dividing by dt squared, right? Delta t squared. And so delta t squared, if we take that outside of the square root, it just becomes delta t. So that's the delta t that comes out. So this is kind of like, again, nothing too formal, but this is more or less how this formula comes about. And there's a formula for the arc length if you're given just a function, but here if we're given a parametric equation, this is our formula. So that's just one length, and then we add them up, and you know, when you add up a whole bunch of things, it becomes an integral. So that's our formula right here. So let's do an example. It says to set up an integral that represents the length of the curve, and then use your calculator to find the arc length. So a lot of times when you're looking at arc length formulas and finding the arc lengths of things, because of the square roots and the squares and stuff that's happening in there, chances are you're going to get an integrand that's going to be difficult to solve by hand. And so a lot of these problems that you'll see in your homework will have you just set up the integral and then maybe compute it using your calculator. So in a test situation, you're most likely just going to set up your integral and not have to solve for it. All right. So let's do this example. And I think it's pretty straightforward once we have the formula. We want the derivative of x and the derivative of y with respect to t. So let's find x prime of t. This is 1 plus 1/2 t to the negative 1/2. And then y, it's almost the same thing. Y prime of t is equal to 1 minus 1/2 t to the negative 1/2. And then we can just put all this into one integral. So the arc length is going to be, they call it S, I don't know if they call it anything, L. Let's call it L. We have limits 0 to 1. Most of the time they'll give you the limits, in which case it'll be a piece of cake, and sometimes they'll have you figure out where it intersects a couple of places, and so you might have to do a little bit of work to find the limits. But it's important that you look for t values here. These are t limits, and it's going to be the square root of 1 plus 1/2 t to the negative 1/2 quantity squared plus 1 minus 1/2 t to the negative 1/2 quantity squared. I'm sure if we worked this out and simplified it, it would be something that might actually be manageable if you were to try to attempt to do this integral by hand. But I'm not going to do that. You guys can try to figure it out. I'm just going to see if I can just go ahead and use roll from alpha. So that's 1 plus 1/2 t to the negative 1/2. Close that and square it. Plus the same thing. With a minus. Suppose we can close that to 0 to 1. And it's always nice to kind of look at it and graph it just to see if it makes sense. If my graph is like, you know, within the squares 0 to 1, and then I get like 2,000 as my arc length, and I know that might be wrong. So it's probably good to try to graph this as well. So this is my curve. Just by looking at it, can you give me an estimate of what it's about? What? A little bit bigger than 2, right? So we should get an answer that's a little bit bigger than 2. It didn't happen. Parentheses. So 2.09, a little bit bigger than 2, right? So those are the things that we want to kind of watch out for. When you're doing homework, you have the power to graph things with some sort of graphing program like Desmos or whatever else you might be interested in doing. And so you can always check your work to see if it kind of would make sense. And in this case, it looks like it does make sense. Okay. Example that I did after class, I had a value of 24,900. And so I said, whoa, that's kind of big. But then I looked at the graph, and the graph was going almost up to 2,500, so, or 25,000. So that made sense to me. So those are some of the things that you can watch out for. You can try to graph it and see if your answer makes sense. Any questions? All right. So it's really nothing but a formula. Speaking of nothing but a formula, imagine taking this arc length and then spinning it around an axis. And so that's the surface area of revolution. You guys should have been familiar with things rotating around. Except before you were looking for volume. And volume seems to be a little bit easier. But here you're going to look for surface area. So this is something that's being spun around the x-axis, and then there's something equivalent if you're spinning around the y-axis. And let's see if we can do a problem similar to that. But the idea here is that if you have a curve, then you're spinning it around some axis, x-axis in particular. And you're looking for the surface area, then the surface area looks almost like a cylinder, except depending on how the thing curves, how your curve curves. It might not be a perfect cylinder, but we're going to use cylinders to approximate, which is what one of the powers of integrals is, that we're just using approximation, and the smaller those delta x's or delta t's get, and the closer it is to the exact value. So imagine having a little piece of surface that you're looking at, and then pretending that it's a cylinder. We know the surface area of the cylinder, right? What's the surface area of the cylinder? Radius r, height h. I'm asking for the surface area of the cylinder, and you guys are just nodding. At least a few people are nodding. What is it? Tell me. What? 2 pi r h, right? Surface area. So area of cylinder is 2 pi r h. So we just need to figure out what r is and what h is. Yeah. Yeah, that's all you want, because you're going to add up a bunch of sides of cylinders. You're not considering the top and the bottom. So the side of the cylinder is 2 pi r h, and the radius looks like it's going to be some y value. So that will end up being your radius. And then the height here, well, the height is going to be the length that we're looking for. Okay? And then the arc length has a built-in delta t because the t-axis is actually not in this drawing because it's being brought in from somewhere else. So we have 2 pi r h. And then we just add up a whole bunch of these sides of the cylinders, and then we have the total surface area. Okay, so that's where that formula comes from. And now that we're okay with that, where that formula comes from, let's do a problem. Which one should we do? Let's do the first one. So let's find this the surface area of this thing being revolved around the x-axis. So I think we just need some derivatives, and we just need to use a formula. So x prime is going to be, derivative sign is cosine or negative cosine? Cosine. And then the derivative of y is going to be positive cosine 2t times the derivative of inside. This is chain rule. So throw that 2 out there. So now we have the derivatives, and then we're just going to use a formula. So S, surface area S, is the integral from 0 to pi over 2. Again, they give you the limits. Makes it nice and easy for us. We have a 2 pi constant that we probably should have put outside of the integral, but what's in here right now. So we have the sine of 2t as the y value, and then we have the square root of the derivatives. We have cosine t squared plus, and then 2 cosine 2t squared dt. Okay, and that's it. That's the setup. If you know your double angle formulas, maybe you might be able to find something here simplified and then use some trig identities. But if you just punch it into a Wolfram alpha, then we're all good. Okay, any questions? So I won't do that. Maybe I'll have it extra in our notes later that you can download eventually. But let's move on to, I think this is it for this section. So we're going to move on to 10.3. Questions? Yes. Probably not. So test situations, I'm more interested in having you guys set up the integrals instead of solving them, because presumably you guys all took Calc 2 and you guys already know how to solve them. I'll just assume that. Yeah. Oh, the difference is that your radius now is going to be an x value, right? So remember how we got this formula, or how I kind of talked about explaining this formula. Your radius here, I should have done green. So your radius is the y value. And imagine spinning this around the y-axis, and then your radius is going to be an x value. Now, I don't think they're going to get fancy and have it spun around like a different axis like you guys did in Calc 2. But if there is, you just look at the measurement of the radius from the center of rotation to however far that curve is, and then that's going to be your radius. The height will always be the arc length because we're looking at the arc length that's being spun around. So the only change would be instead of a y, you'll have an x. Any other questions? Okay. All right, let's move into the new chapter or new section. And we're going to study polar coordinates. Now, look, I have objectives. All right, we'll start off with a polar coordinate. With the polar coordinate equations, well, what's the objective? Explore a relationship between polar and Cartesian coordinates, graph polar equations. So we'll probably explore families of polar graphs and explore a relationship between polar and parametric. So we'll probably get through the 3 bullet points here. I don't know if we'll get to the relationship between parametric and polar, but let's see how far we can get. So we have the relationship between polar coordinates and Cartesian coordinates is actually 2 equations at a time we would look at. Let's push these over a little bit. So I think more commonly, when people think of polar coordinates, they think of this equation, or these 2 equations. X is equal to r cosine theta and y is equal to r sine theta. And that might look familiar because that's how we kind of look at circles and stuff like that. But it really does come from circles and trig. So if you think of r as the angle or as the side that makes the angle theta in your unit circle, that doesn't have to be unit circle. In fact, this is because it's r, it's not a unit circle. Then you have r and theta, then you can look at x and y as either the adjacent of or the opposite sides of the angle. And so you can have your triangle and everything kind of relates back to the this is your x, this is your y, and now you have the relationship of opposite over hypotenuse and adjacent over hypotenuse related to the sine and cosine. Okay. So the interesting part is this other set of equations over here. The r squared is equal to x squared plus y squared. That's like the equation of a circle. And then the tangent of the angle is equal to y over x. So I think this will allow us to go between Cartesian coordinates and polar coordinates and Cartesian coordinates. So what is polar coordinates anyways? Have you guys heard of polar coordinates? Have you guys seen polar coordinates? We have graph paper in Cartesian coordinates. And the graph paper in Cartesian coordinates kind of looks like, you know, the graph paper that you would get. And so you would move along the x-axis and the y-axis depending on what your point is. You would move along the x, and move along the y, and then you get to that point. So sometimes this is referred to as rectangular coordinates because, well, you're getting rectangles and stuff. So a polar coordinate graph paper, which you can purchase somewhere, or you can Google polar coordinate graph paper, would be r's and thetas. And r would stand for what? Radius. So take a look at radial distances, and then theta would stand for the angles. I guess it wouldn't stand for it. It would mean the angles. And so your polar coordinate graph paper would have circles. Well, yeah. And angles. And so a point in polar coordinates, if your r and theta points would be like 2 comma pi over 4, you would say, I want to go a radius of 2, so I'll go 2 units, 1, 2, and then I would go an angle of pi over 4. So 2 comma pi over 4 would have a radial distance of 2 and an angle from the positive x-axis of pi over 4. You guys have seen those graph papers, right? I mean, you can Google polar coordinate graph papers. What? There's what? Oh, Desmos, yeah. Should have just copied and pasted one of these instead of. Oh, my drawing looks pretty cool. All right, so how does this happen? So that's the relationship between the x and the y, and you can go back and forth. If they have 2 comma 4 or 2 comma pi over 4, and say I want to find out where that is over here in Cartesian coordinates, since I have the r and theta, I probably want to use the first set of equations here, right? You just plug in the r and plug in the theta and see what you get. So if I plugged in the r and theta in here, x is going to be equal to what? What's r? R is 2 cosine pi over 4, and y is equal to 2 sine pi over 4. So root 2 over 2 times 2 is just root 2. So then I would be equivalent to this point, root 2 comma root 2. So this point in Cartesian coordinates is the same as root 2 comma root 2. No, I'm sorry. The 2 comma pi over 4 in polar coordinates is equivalent to root 2 comma root 2 in Cartesian coordinates. Okay. All right. So now let's look at functions in polar coordinates and see how it's drawn. Let's take a look at a simple function like a constant. If we take a look at a function, a constant function, usually we think about this as f of theta. Instead of saying y is equal to f of x, we would say r is equal to f of theta. R is equal to 2 is a constant function that doesn't depend on theta. So that is to say, it doesn't matter what my angle is, my r is going to be 2. What do you think this is going to look like? It's going to be a circle. And the idea here is that you would have see if I can do this here. They have arrows here? Do you guys use OneNote? Oh, there we go. Ah, whatever. Anyways, the idea is that, what's the idea? The idea is that as theta changes, you're going to rotate this around. And as you rotate this around, the length's not supposed to change, but it keeps changing. As you rotate that around, you're going to draw out the radial distance that this has. And in this case, since the radial distance is a constant 2, r is equal to 2, the length of this arrow is not going to change. That arrow is called a ray, by the way. The length of ray isn't going to change. So the graph of a constant r is equal to 2 is just going to be a circle, radius, whatever 2 is. Now, we can also use this relationship between r and theta to see if we can express this as an equation in Cartesian coordinates. So r, remember, what's r equal to? R is equal to 2, but r equals x plus, over cosine theta, but let's use this one now. So we can replace r with the square root of x squared plus y squared is equal to 2. And because the square root looks a little clumsy, let's just square both sides, and then you have an equation of a circle of radius 2. So again, there's a relationship between x's and y's, Cartesians and polar coordinates, whether you're looking at just points or a whole equation relationship. And then the graph should be the same. All right? So in Desmos, like Matthew was saying, where are we? There you go. R is equal to 2. Pretty straightforward. Okay, so let's do more graphs. Theta, whoa, I'm used to looking at, let's think about x's and y's again. Y is the dependent variable that's dependent on x. So x is usually what you put in. So we're used to seeing y equals f of x, right? And then when we saw r is equal to 2, we got a circle out of it. And I want to get your mind thinking back at the at the graphing paper. I really want to replace that polar coordinate graph. No, okay. Just seems more personal then. So in Cartesian coordinates, let's look at the Cartesian coordinates, and I say y is equal to 2, what would you draw? So straight? I mean, a line is a straight line, but a horizontal line, right? And so when you that looks like it's one of the grid marks, right? If you just go up along grid mark. Now, if I say x is equal to 2, what would you draw? A vertical line, right? So if you look at the grid marks for Cartesian coordinates, it's either horizontal lines or vertical lines. And those are dependent on whether you're looking at an x value or a y value. And that's what happens when x value is constant or a y value is constant. Now, if you look at the polar coordinate graph, we kind of established that if you have r is equal to a constant, then it would look like a circle, right? When theta is a constant, what do you think it'll be? A straight line at that angle, right? And that's like the other type of grid marks that happen in polar coordinates. In polar coordinates, you have circles and lines passing through the origin. And those lines passing through the origin represent the angle that it makes. So the graph of theta is equal to pi over 3 should be a line passing through the origin with an angle of pi over 3. Whatever pi over 3 looks like. I think it's a little steeper. And that's how your graph would look like, yeah? No, because it doesn't depend on r. And r would be kind of like your direction. We haven't dove, we haven't dove, is that the right word? We didn't dive into that yet. But we will in a second, or in a minute, or 5 minutes, yeah.
If the line goes past the origin, is the angle of that section of the line making not equivalent to pi over 3, or do we not care about that?
If the line does not go through the origin?
No. Since the line is going through the origin, let's just look at like the bottom section of it.
Yeah.
That part of the line is not making an angle pi over 3, so would the line not stop at the origin?
I don't understand what you're asking. Draw.
Okay. Yeah. Okay.
Yeah.
So what I'm saying is, if we got this line and then its polar coordinates, this angle is not pi over 3. I mean, even though it's 180.
Oh, okay. I see what you're saying. Yeah.
This isn't pi over 3. Is what I'm saying.
Yeah.
I'm asking why we're continuing the line past it.
Okay, that's kind of equivalent to the question. No, it's just a good question. So, again, because r, it's independent of what r is equal to. It doesn't matter, and it looks like your graph. What is this angle, anyways? 4 pi over 3. So the graphs of theta is equal to pi over 3 and theta is equal to 4 pi over 3 would be the exact same graph. Again, independent of what r is equal to, you can let your r go positive, negative, and then that would draw out every single point on this line. And if you're doing pi over 3, you would be pointing that way. So it turns out that depending on which way your ray is pointing, that's the positive, and then behind you it's negative. So pi over 3 will be pointing towards the first quadrant, but since it's independent of r, it's going to cover everything behind it in the third quadrant. So if that's what your graph is, that's what it's going to draw. Now, if your graph is theta is equal to 4 pi over 3, then your ray is actually pointing the opposite direction, which will cover everything in the third quadrant, but the negative r values behind it would also be covered, so you're graphing the same line. Okay? All right. Instead of what? Oh, 7? Like 5? Yeah. Wait, angles and what? Numbers instead of angles. Okay, yeah. So, and remember that your radian measurement is just a number, and pi over 3 and pi over 2, you can punch that into calculators and figure out what they're equal to, right? So when I say, or when I ask you, or if I ask you to graph theta is equal to 1, you just have to figure out what angle it is. And so 1, I think pi over 4 is a little bit less than 1. And pi over 2 is 1.5 something. It's bigger than 1. So I would say that this is a line that's between pi over 4 and pi over 2. Okay? Less, it's even less, so it's less than pi over 3. So I could say that this is pi over 4, and this is pi over 3. And so theta is equal to 1 is somewhere between that. Was that what you were looking for? Oh, degrees? Let's not do degrees. Unless we really, really have to, but in general, let's just stick with radians. Oh, doesn't want to graph it. I thought it was going to graph it. Is there a polar coordinate function in Desmos? The settings? No, it still doesn't help me graph this. Well, that's not what I was looking for. Anyways, I think this might do it. Let me see. There he goes. So again, depending on what R, I don't know if you guys can see that little top corner over there. R, this is the range for my R values. I can have it go -5 to 5, and then I would get, you know, a longer line from R is equal to -5 behind it, and R is equal to +5 in front of it. So theta equals to 1 would be a line that's a little bit angled, a little bit steeper than the first one. In fact, what do you think theta is equal to 100 look like? So as you're thinking about this and trying to give me an answer, what are you thinking to try to answer my question? How many radians it is, right? So I think 6 divided by 6.2, 6.3, and then it'll give you some idea at least where it is. That looks like it's going to be, well, I don't know if it's in the second or fourth quadrant. It's in one of those quadrants. But I could tell if I shrink R, oh, it's in the fourth quadrant, right? So theta is equal to 100 radians is going to be somewhere in the fourth quadrant. And I guess we can play around with this with a slider. All right, so theta just controls the angle, and that kind of makes sense. All right, let's take a look at some more graphs. R is equal to theta. What do you think this is going to look like? So imagine our grapher, right? If you're graphing this, what you would do is you're like Ray, and you're going to start with a positive x-axis, and then you're going to spin around from 0 to 2 pi and go farther if you need to or want to. And then your R will just go forward larger or smaller depending on what the function says. And if it goes negative, by the way, you go backwards from where you're pointing. So if you are R, your ray, and then R is equal to theta, theta is equal to 0, what's your R going to be? And when theta is equal to 1, what's your R going to be? And we have an angle 1, right? We know what that angle is, somewhere in the first quadrant. Theta is equal to 2, what's your R going to be? 2. Can you picture what's happening? What is it? It gets big, so spiral. So if we put in those points that we were just talking about, at 0 and at 1, now what we're looking for is like a radial distance of 1 unit when you make an angle of 1. And then 2 is somewhere in the second quadrant, and you'll have a radial distance of 2 when you make an angle of 2. And so what that's going to do is going to trace out this thing that gets larger as you go around in a circle. Okay, that's going to be a spiral. Now in Desmos, I guess it'll grow really quickly unless I multiply it by like a half or a third or something small. But if we try to draw it in Desmos, whoops. Kind of looks like that. Okay. Yes. That was something separate. We can insert the golden ratio here. You guys know what the golden ratio is? 1 point what? 1 plus root 5 over 2. Like one of those special numbers like pi. Among other things. What's that? So any function that's an increasing function will produce a spiral. And this, by the way, if you look at this, theta goes from 0 to 12 pi, it says here. And that's part of the picture that you're seeing. Yeah? Oh, what do you think happens when you have a negative theta? Ah. Well, remember the negative numbers go behind you, right? So let me get this inserted in our notes first. Ah, come on. So if we take a look at our program, our Desmos, and then instead of going from 0 to 2 pi or 12 pi, let's go from 0 to pi, just to see how it looks like, right? And then now imagine going negative. If you go in a negative direction, your array will be going downward in the negative angle, and then your R values would go negative. So we can imagine how that might look like. Let's go from negative pi to pi, or let's go from negative pi to 0. So if you imagine that being drawn out in a negative direction, you're drawing your graph in the opposite of where you're facing. And so if we go from negative 2 pi to 2 pi, you get like a cool looking picture. So you can figure out which one's the positive graph, which one's the negative graph. Actually, let's take a picture of this picture. Oh, but then if you see the other picture, then you know which way to go. Okay. So what part do you think is the positive theta and what part's the negative theta? Now, I guess we can see the positive theta already. Let's identify the negative theta. So negative theta would, think about your theta pointing down this way, and that's a negative small angle. And so that would bring you to this side over here. Okay, negative theta. Okay, good. All right, these three graphs are kind of cool. They're in a family of what's called a cardioid and les maçons. Somebody speak French here? I thought somebody spoke French one day after class. Anyways, let's just draw them out. I think it's kind of fun to draw this out first in Cartesian coordinates. Like, let's take a look at this. 2 cosine, so the cosine goes like this. you stretch it 2, and then you reflect it. So that's a negative 2 cosine theta, and then you move it up by 1. You got all that? All right. So then your graph is going to start at 1. Your graph is going to start at 1, and it'll be cosine, except it'll be negative. And then it has an amplitude of 2, so it goes as far down as -2. And then back up to pi. So what you could do is you can think about how this is going to be drawn by looking at the graph in polar coordinates. When you have your angle at, oh yeah. Oh yeah. 1. Miguel, yeah. All right. So you start off pointing in a theta is equal to 0 direction, and what's your R value? So you can put theta is equal to 0, or you can just look at the graph. R is going to equal to 1. So we have a 1 here. And then by the time I get to pi over 2, I go negative for some reason. And so there's some angle here where I have to, your R goes to 0 and goes negative. And so what's going to happen is that it's going to do something like this, and then will become negative after that. So it becomes negative down here, and then it has a value of -1. And then it'll come back to 0, and then it'll be positive again. And then it's going to have the high value here at, what is this? 3 pi over 2. So 3 pi over 2, you'll get down to, oops, what happened? You'll get down to a height of 3, and then you'll come back. Okay. So this graph is called the cardioid because it looks like a heart. This is a cardioid with a little loop. It's called the limaçon. And the C has a little, I don't know what letter that is in French, but it's called a C. Just making shit up. So if we take a look at those graphs, R equals, what was that? 1 minus 2 cosine theta. Oh, it's sideways, sorry. Is that right? Yeah. What did I do wrong? This graph? Oh, this is a cosine graph. I mean a sine graph. This is a sine graph. Sorry, my bad. I'll have to change that in the notes. So anyways, it's actually a sideways. Actually, the cosine's a sideways cardioid of limaçon, and then the sine is up and down. So I don't know why I didn't catch that. But let's do 3 minus 3 cosine theta. Just to show you the pictures, and I'll paste it. Oh, that's the wrong one. R equals 3 minus 3 cosine theta. Uh-oh, what's going on with my graph? Something happened. So it's like a cardioid. And then the other one was something similar. It was 3 minus 2 sine theta. Which one? 3 plus 2 sine theta. So it's another cardioid shape, but except it doesn't go all the way up to make that really sharp cusp at the origin. Okay, so I suggest that you play around with these types of polar coordinates. There's a family of them. The last one that I didn't get to do is actually fun, so you guys should try to put that into Desmos. We're done. Are we done at 50 or 55? 2 o'clock. Let's stay here at 2. Well, let's be done for today. I'll put the notes up and the videos up again. The videos will probably come tomorrow, but and we'll have a quiz sometime this week too. I don't know when yet. Maybe tomorrow. Okay. So everything that we've done so far, like parametric equations and stuff. Probably not. If it's tomorrow, it won't be this.